Today we are going to discuss about double stub matching. In the previous lecture already we have seen single stub matching input impedance. Now we will see the double stub matching. So first of all, we know what is meant by a stub. Stub is a short section of a line which is connected to the transmission line to reduce reflections along the line. So a short section of a line is connected to the main transmission line to reduce the reflections along the main transmission line, and it can be classified into two types. One is a single stub matching and second one is double stub matching. So in the single stub matching we have some drawbacks are there. So the drawbacks of this single stub matching are, we will see the disadvantages. Of single stub matching. The first one is it is used for single frequencies only. It is used for single frequency. If the frequency is changed, then the location of the stub, has to be changed. See here, we have a main transmission line and it is ended with a load ZR, and here we have a single stub, a short section whose length is LT and the location of the stub is LS. So this single stub is useful for only at single frequencies. If the frequency is changed, then automatically the location of the stub has to be changed, and it is also a narrow band system. It is also a narrow band system. The single stub matching system is useful for a fixed frequency only, because as the frequency changes, the location of the stub will have to be changed. The change of the susceptance of the stub does not present at any problem because the shorting plug may be moved to the required position. So the single stub matching is a narrow band system. So this is one disadvantage of single stub matching. And coming to the second disadvantage, it will give inaccurate results. When used in coaxial cables. When it is used in coaxial cables. So this is another disadvantage of the single stub, that is, for final adjustment of the stub has to be moved along the line slightly. This is possible only in open wire lines, and therefore on coaxial lines single stub matching may become inaccurate in practice, though it reduces the reflections losses in a considerable extent. To overcome the two disadvantages of the single stub matching, two short-circuited stubs whose lengths are adjustable independently but whose positions are fixed, so we consider this as a double stub matching. So this is a main transmission line ended with load ZR, And first of all, we are considering a short section of stub 1 positioned at A and whose length is LT1, and the location of the stub is say LS1. And similarly, we are considering another second stub at position B whose length is LT2 and location of the stub is LS2. Here the location of the two stubs are fixed, whereas the lengths of the stubs can be changed independently. Here the location of the stubs are fixed, but coming to the lengths of the stubs, these are changed independently. See here, this is a main transmission line whose characteristic impedance is Z0, and this is a stub. It is also having the characteristic impedance Z0, and this is the second stub. It is also having the characteristic impedance Z0. And now we are considering the first stub whose length is LT1 be located at the point A at a distance of LS1 from the load. So now we consider the normalized input admittance at that point. The normalized input admittance for the first stub. Generally we know that the input impedance for a lossless transmission line, the input impedance Zin is Z0 times ZR plus ZZ0 tan beta L by Z0 plus ZZR tan beta L. If you write the ratio Zin by Z0, it will becomes ZR by Z0 plus J tan beta L whole divided by 1 plus J ZR by Z0 tan beta L. This ratio, the input impedance by the characteristic impedance ratio, is called normalized impedance, which is represented with a small z in. So the small z in is equals to, where this ratio ZR by Z0 ratio is represented with the normalized load impedance ZR plus J tan beta L divided by 1 plus J. This ratio is also the normalized load impedance ZR tan beta L. If I write 1 by Zin, so that means if I write this one as Zin as 1 by Yin, then ZR is also can be written as 1 by YR plus J tan beta L divided by 1 plus J 1 by YR tan beta L, which can be written as, here YR is LCM, so that we can write this one as 1 plus J YR tan beta L divided by, here also YR is LCM, then these two YRs will get cancelled, so YR plus J tan beta L. So Yin is YR plus J tan beta L divided by 1 plus JYR tan beta L. Now rationalize this one. So that we get y in as yr plus j tan beta L divided by 1 plus JYR tan beta L is multiplied with 1 minus JYR tan beta L divided by 1 minus JYR tan beta L. In the LCM, in the denominator, we get a plus b into a minus b formula, so that a square minus b square. So if you multiply these two terms, you get a real term and imaginary term. yr minus j yr square tan beta L plus j tan beta L plus yr tan square beta L, the whole divided by 1 plus yr square tan square beta L. This is y in. So y in can be written as, the real term is yr plus tan square beta L is the real term, divided by 1 plus yr square tan square beta L plus the imaginary term j tan beta ls tan beta L minus yr square tan beta L divided by 1 plus yr square tan square beta L. So this is the real term and this is the imaginary term. Now the admittance is nothing but G plus JB, where G is the conductance and B is the susceptance. And here at this location, at location A, generally this YA admittance at position A, so this can be written as a GA plus JBA. B is the susceptance for a stub which is placed at position A, so which can be written as, so this is YR plus YR tan square beta LS1, where it is positioned at point A, so that the length of the location of the stub is LS1 here, divided by 1 plus YR square tan square beta LS1. And similarly the imaginary term is 1 minus YR square tan beta LS1 divided by 1 plus YR square tan square beta LS1. See here, the main important point is the first stub changes only susceptance JB1 here. So the overall input admittance YA dash, it can be written as GA plus JBA dash. And similarly the second stub is located in such a way that the admittance is 1 plus JBB, so that this YB will becomes 1 plus JBB. See here, at position A, at the location A, YA is GA plus JBA. So this is the input admittance at this position, position or location A, and this is the stub location. So here the stub location is having some first stub changes, only the susceptance is JB1. Here the first stub is having the susceptance JB1. So after adding this JB1 to the admittance, so that it will becomes YA dash is equals to GA plus JBA dash, where this susceptance changes. And again at this position, now this is YA dash. YA dash is nothing but GA plus JBA dash, and the second stub is located in such a way that the admittance is having 1 plus JB. Here the admittance is 1 plus JBB, and now we are choosing the susceptance of the second stub as minus JBB. The admittance at this position is 1 plus JBB, and the stub is having the susceptance minus JBB. So now after adding the second stub, the overall YB dash, the admittance YB dash will becomes 1 plus JBB minus JBB, where this is the susceptance of the second stub, and at point B this is the admittance of the transmission line. So when you add the second stub, automatically these two will get cancelled and YB dash will becomes only 1 here. So the main principle is to transfer the maximum power from source to load. So we are providing the susceptance of the second stub as minus JBB, and at this position the admittance is 1 plus JBB, both will get cancelled. And the overall concept is, so only the conductance term will becomes 1 and all the imaginary terms will get cancelled by this location of the stubs here, so that the maximum power will transfer from source to the load